Assalamualaikum and hi, my name is Roman Imam. Today I will be starting my presentation for Torricelli's law experiment from introduction. So, fluid dynamics plays a crucial role in understanding the motion of liquids in various engineering applications. One fundamental principle is Torricelli's law, which describes the relationship between the velocity of fluid flowing out of an orifice and the height of the fluid column above the orifice. This experiment aims to verify Torricelli's relationship by comparing the theoretical and experimental velocity of water flowing through an orifice in a cylindrical tank. To achieve this objective, key parameters such as the initial water level in the tank, maximum water trajectory distance, and the height from the ground to the center of the orifice are recorded. The theoretical velocity is derived using Torricelli's equation, while the experimental velocity is calculated from trajectory measurement. Next, the objective of this experiment is to verify Torricelli's relationship by comparing the measured and theoretical velocity of water flowing out from an orifice in a cylinder tank. So for the scope, number one, the experiment will be repeated for three different heights of the orifice, which is 36.5 cm, 56.00 cm, and 77.0 cm. Number two, test with 5 different volume of water with 2.0 liter, 1.75 liter, 1.5 liter, and 1.25 liter, and 1.00 liter. Alright, next for the theory. Torricelli's theorem, which is Torricelli's law, is a fundamental principle in fluid dynamics derived from Bernoulli's equation. It states that the speed v of a fluid flowing out of an orifice under the force of gravity is equivalent to the speed that a free falling object would have if it fell from the same height h as the fluid column. So the equation is v equal to square root 2gh, where v, velocity of the fluid exiting the orifice, g, acceleration due to gravity, 9.81 meter per second or 29.81 meter per second square. H is height of the fluid column above the orifice. Okay, for the working principle. Bernoulli's principle, the theorem used Bernoulli's equation, which state that the total energy per unit volume in a streamline flow is constant for a stationary tank with an orifice. The equation is P plus 1 over 2 rho V square plus rho GH equal to constant. So the key assumption is the fluid is incompressible, the flow is steady and irrotational, the tank's surface area is significantly larger than the orifice, making the velocity at the surface is negligible. So for the application, we have
our experiment setup. We have crane marker and cylindrical cylinder and measuring tab. And we also have a measuring cylinder to collect the water volume V1. For the procedure, the first step is the path was placed on the floor. A measuring tab was set to maximum and pressed on the path. The ramp with adjustable platform height was pressed at the zero end of the measuring tab. The cylinder with drill hole, which is orifice, was placed on the platform with the height from the floor to the center and the orifice in the cylinder wide as 36.5 cm. Without changing the volume of wire, the cylinder position on the platform was adjusted to ensure the orifice was aligned with the scale of the measuring tab. The orifice was covered with clay to avoid the water flowing out from the orifice. Water with volume of 2 liters was poured into the cylinder. The initial water level H in the cylinder was measured and recorded. The clay that covered the orifice was removed. When the water started flowing out, the stopwatch was started immediately to measure at the time taken to drain out the water in the cylinder T. The first landing of the water flowing out from the orifice onto the path was marked out by the crane marker. The position of the crane marker was measured and recorded. This will be volume to the maximum water trajectory distance as S. The stopwatch was stopped when the water had stopped flowing out from the cylinder. The stopwatch reading was recorded from the result T. Step 3 to 7 was repeated twice to obtain the average result, and step 3 to 8 was repeated with the volume of water 1.75 liter to 1 liter. Step 1 to 9 was repeated with the volume of 56 cm and 77 cm.
Okay, so now I will explain about the result. So the volume of water in liter that we use in this experiment is from 2 liter to 1 liter, and the initial water level H, the average is this one, and the maximum water trajectory distance X, the average is this, and the time taken for the water to drain out T, the average is this. So the water flow rate Q is equal to the volume of the water divided by the time taken for the water to drain out. So the volume of water is in the liter, so need to convert to the meter cube. And the velocity of the waters is the H divided by T. So it's the initial water level divided by the time taken for the water to drain out. So the table 1 is the Y equal to the 0.365 meter. And this one is also used the previous method, and the Y is equal to the 0.560 meter. And this one is also used the previous method to calculate the Q and the velocity. And this one is table 3, which is the Y is equal to the 0.770 meter. So now I will explain about the first discussion, and the question is explain your selection on dependent, independent, and constant variables. So for constant variables in this experiment is the fluid type, which is the water, remain constant to ensure consistent properties like the density, viscosity, and incompressibility. This allows accurate use of Bernoulli's and Torricelli equation. And the independent variables are initial water level in the cylinder H and the height from the floor to the center of the orifice in the cylinder Y. So the dependent variables are maximum water trajectory distance x and the time taken for the water to drain out T. Using Torricelli equation, V is equal to the surd 2gh, the outflow velocity depends on h. Changes in h and y directly affect t and x. Both x and t variables are results that will have the obvious change when the dependent variable change. So the t is the time taken for the water to drain out, and the x is the maximum water trajectory distance.
Alright, for the discussion part, I got the question of clarify on how you can relate the Bernoulli equation with Torricelli law for this case. Show all the derivation and explain each step. So from Bernoulli equation, as you can see, from figure shown, both point 1 and 2 are exposed to atmosphere, and point 2 set as datum line. Therefore, we can assume P1, P2, and Z1 is 0. The area of the water surface is much larger than the area of the orifice. Therefore, V1 also assumed to be 0. Therefore, the equation is simplified into H equal to V2 square over 2G. Rearrange for V2. V2 equal to square root 2GH. Both Bernoulli equation and Torricelli law shown the same result for V2, prove that they are related.
The second discussion of our experiments is discussed about the percentage of relative error of theoretical and measurement values. The theoretical value of V can be calculated by using the Torricelli equation, which is V equal to square root of 2GH, and the experimental value of V can be calculated by using the equation of V equal to X times the square root of G divided by 2Y, and the percentage of relative error can be calculated by using the absolute difference between theoretical value and experiment value divided by theoretical value and times 100%, and this is all our calculated result. As a result show, when y equal to 0.365, it have the highest percentage of relative error, and followed by y equal to 0.560, and when y equal to 0.770, it has the least value of percentage relative error, which is only 1.49%.
The last discussion is the source of error and method to minimize the error. So the first error is the parallax error, which occurs when measuring the maximum water trajectory distance. Solution is ensure the observable ice level is perpendicular to the measuring tab when reading the x. So the second error is the orifice leakage. Small water leakage from the orifice caused by clay reduce the initial water level h before the experiment starts. Solution is to use a rubber stopper instead of a clay to seal the orifice and ensure no leakage. Wait for the water to climb before measuring the h. And the third error is the air resistance. So the air resistance slightly alter the trajectory and velocity of the water jet when water exits the hole. So the solution is to conduct the experiment indoor and closing all the windows and the doors. Okay, so in conclusion, by comparing the mass and theoretical value of velocity, this experiment seeks to validate the Torricelli relationship. In order to achieve the experiment goal, a cylinder filled with a specific volume of water was set up on a platform that will rise from the floor to the cylinder on feet at 0.365 meter, 0.560 and 0.770 meters. This allows the water to flow out of the cylinder. The theoretical and experimental value for the velocity of water flowing out from the cylinder prefix V were obtained by measuring and recording the initial water level at the cylinder H, the maximum water trajectory distance X, and the time taken to empty the cylinder T. Table 1, 2, 3 display the data collected for this experiment. According to our results, the average percentage of relative error for the experimental and theoretical value of V when y is 0.365 meter, 0.560 meter, and 0.770 meter are 4.93 percentage, 1.99 percentage, and 1.49% respectively.
And the safety procedure of our experiment is, in this experiment, we shall keep up on the electrical device, wear the eye protection, keep the floor dry, wear a lab coat during the experiment, follow all the instructions and use proper equipment. And this is all our reference for our experiment. And this is the primary data we get from our experiment.